Welcome back to Soggy Tucson. We're not only experiencing Newton's laws in the classroom, but we're experiencing Newton outside in terms of the weather, but hopefully we will be dry in here. And just some reminders, homework number 1 is due on Sunday, the 11th. And office hours on Thursdays have been changed to 9 o'clock. Today what I want to do is actually go through a transfer function from a block diagram. We'll go through the block diagram algebra. And then when we start into connecting these different ways of modeling systems, when we get into the transfer function, we'll actually work through a Mason's gain formula, which is a different way of really doing block diagram algebra, but it's built into the process of performing Mason's gain. But in terms of the representations, I want us to be comfortable with either any of these representations. If you start with a state space, can you transform that into a block diagram? Can you take a block diagram into a transfer function? Can you take a transfer function into a differential equation? And if you can go that direction, we can start with differential equations and put those into a block diagram, which we could then create a state space representation. So you can see how you can get back and forth with all of these different ways of modeling or representing a particular system's dynamic behavior. And they're not particular to whether it's a mechanical system, an electrical system, an electromechanical system, any system, a thermal system that you have. If you can express it in one of these forms, you can now translate it into one of the other representations. Let's then start with the following example, which is single input, single output. And I'm drawing it so that you have time to sketch it also if you want to follow along. Here is our reference input. The circles are summing junctions. And the blocks are typically some kind of system or subsystems transfer function. And this is a little bit more complicated than our cheer, our second cheer. Our second cheer, if I could cover things up, you could sort of see G1 and H1 are in this feedback configuration, but in this particular diagram we have a feed forward path from R into the second summing junction. We have a feedback of H2 all the way around G1 and G2 feeding back into the summing junction. And this is a little bit more involved than what we've dealt with before. And what we want to do is utilize block diagram algebra to come up with the transfer function between the input R and the output Y. We're looking for T of S. And that means really that we want to, if we're starting to write equations, we want to eventually have all of those equations in terms of just Y's and R's, and then solve for Y in terms of the R's. And last time, what was one particular strategy that I suggested you might want to employ to work these? Okay, so we may want to be labeling the outputs of the summing junctions, label that signal, and write some equations in terms of those labeled signals that are the outputs of our summing junctions. Let me go ahead and label this E1, that's a signal coming out of the first summing junction, and this one as E sub 2. And the reason I'm using E is a lot of times we might refer to those as an error type signal. That's where the E is coming from. But there's no real special reason why those are given E's. They didn't fail coming out of that summing junction. Sorry. They're subscripted anyway. Do you have any E's that are ever subscript? Well, you guys never had an E, so we'll just move on. First, let's start with the output and work our way back towards the input. Let's just say that y is equal to g sub 2 times e sub 2. That's correct. That's a correct expression. Let's start there. And let's try to express e sub 2 as what it is. It's the output of the second summing junction. Let's now identify some description of the inputs to that summing junction. E2 has two inputs that it's made up of. The first one coming in from the top left is simply the input R, and the second input is the output from G1, and G1's output is going to be the system or subsystem G1 times the input to that system E1. So E2 is now R of S plus G1 of S E1 of S. And we seem to be having all these mixes of E's and G's, but we need to make sure that the signals that are present eventually only are Y's and R's so that we can get the transfer function. We now have E1 in that second equation. Let's find an equation for E1 and see if we can write that in terms of Y's and R's. E1 has how many terms making it or creating it? So we have the three signals coming into E1. We have R. We also have minus H1, G1, E1. That's the input coming in at about 5 o'clock. And then we also have an input coming in at 6 o'clock, which is minus H2Y. And that makes up E1. And may I get sloppy and just remove the arguments? This is H sub 2 of S, Y of S, minus H1, G1, E1. I have a couple of E1 terms. I can combine those and actually get rid or get an expression, obtain an expression for E1 in terms of R and Y, and that's what I'm wanting to do. If I pull that last term over to the right or over to the left, and a lot of times I do this alphabetically, so since these are single input, single output transfer functions, they commute. I can make it A times B or B times A, they're equivalent. So I've just replaced H1, G1 with G1, H1. But if these were multi-dimensional, not scalar transfer functions, I couldn't necessarily change the order of their multiplication. But here, this is now, those are the two terms that we're scaling E1, the signal. And on the right, I still have R minus H2Y. And I can now solve for E1. E1 is R, or if I want to, why don't I keep sort of the signals and the systems separated? Let me say it's 1 over 1 plus G1H1, that's times R. And I also have minus H2, 1 plus G1H1 times Y. Now I have an expression for E1 in terms of R and Y. I'm trying to get an equation for the output Y in terms of Y and R. I have Y in terms of E2. If I now replace or rewrite the E2 equation that contains an E1 that now is written in terms of R and Y, I can now have E2 in terms of R and Y. So E2 was R plus G1 times this mess up above, E1, which is in curly brackets 1 over 1 plus G1H1 R minus H2 over 1 plus G1H1. Is that okay? All of this in curly brackets was E1. And E2 was just R plus G1 E1. And now I have E2 in terms of R and Y, and that's what I need to get rid of that E2 in the original equation for the output Y. Meaning now Y is the G2 times that entire collection of terms that make up E1. That's R plus G1 over 1 plus G1H1 times R minus G1H2 over 1 plus G1H1 times Y. I'm getting closer to finishing because now I have one equation that only contains the input signal R and the output signal Y, but I need to really sort of isolate those two pieces. Right now, I have Y sitting on one side, or on both sides, and R's on one side. To simplify that, let me, well, you may not think I'm simplifying it, but let me put all of this over a common denominator. Meaning, I want G2 that multiplies R in that first term to also contain in its denominator 1 plus G1H1. And I can always multiply by 1. Meaning, if I take G2, which is going to be multiplied by R, but if I also multiply that by 1 plus G1H1 divided by 1 plus G1H1, that's still just G2 times R. But the reason I did that is because I want a common denominator in all three of these terms. The next piece is just G1 times G2 over 1 plus G1H1 times R. And then I have minus G1, G2, H2 over 1 plus G1H1 times Y. Ooh. I'm trying to do the algebra so that I can isolate the y terms on one side and the r terms on the other. Let me now clear that denominator by multiplying both sides by the denominator expression 1 plus g1h1. So that now upstairs I have, let me combine all of the terms that multiply r. I have g2 plus this term, which is g1, g2. And I also have the third term, g1, g2, h1, that was coming from that piece. All of those multiply r. And finally, I have my minus g1, g2, h2 times y. I can now pull that last term that contains y to the other side, and I have 1 plus g1 h1 plus g1 g2 h2 times y equaling g2 plus g1 g2 plus g1 g2 h1 times r. And I'm now home. I now have an expression that will allow me to isolate for y over r. Question? So which three terms? I have two sets of three terms. The question was, why are there three terms on the y that scale y or that scale r? So the three terms that scale r, this one is sort of hidden. That g2 multiplies 1, and it also multiplies g1h1. So if I distribute that g2 across those two terms, I get two terms there. And then I have that third term, g1, g2, scaling r in the middle transfer function. Does that help? Yes, so it gets a little bit ornery in terms of trying to keep track of all of your terms, but now we can write down t of s, which is y of s over r of s. I'm going to divide both sides by r and divide both sides by that bracketed expression that scales the output y. In the numerator, I now have g2 plus g1 g2 plus g1 g2 h1, and in the denominator I have 1 plus g1 h1 plus g1 g2 h sub 2, and that is what I was trying to obtain. That's my transfer function, which this could be a ratio of ratios. If my g's and h's are rational expressions of polynomials in S, then in the numerator I have a ratio, and in the denominator I have a ratio, but you could clean all of that up with the appropriate polynomial manipulations, so that when you get all of that completed, you will end up with a transfer function with numerator in S and a denominator in S. And from that, you could identify your poles and zeros of that system. The zeros would be the values of S that cause t to vanish, and the poles would be the values of S that cause the denominator to vanish, or the entire thing to go unbounded. That's block diagram algebra via an example. Let's now try to feel more comfortable with these connections between our different representations or models of the same system. We have state space, we have block diagram, we have transfer function, and we have differential equation. Now we need some object. So think of a pyramid that has four sides, and on each of those four sides you have one of these four two-letter descriptions, and somebody could roll that pyramid and say, oh, give me a representation that's now a BD in block diagram form. Or roll it again. Oh, I want my system representation in state space form. But you should be able to go back and forth with these different representations. Let's start with the one on the left, the state space. Here it's x prime is equal to minus 1, 2, 0, minus 3, x plus 0, 1, u. And let's say our output equation y is a linear combination 4, 5 of x. In terms of our matrices, here is our A matrix. Here is our B matrix, the input matrix. The A matrix is the system matrix. And the output matrix C is 4, 5. And you already know a lot of information just by inspection of this state space representation. If you've had some linear algebra, which most of you should have had from math or from ECE 310, what are the eigenvalues of the A matrix? It's upper triangular, so the eigenvalues are on the diagonal. You have eigenvalues at minus 1 and minus 3. Is this system stable? Your eigenvalues are at minus 1 and minus 3, and those are the same as the poles of the transfer function that you would have from this system. So now you have a pole at minus 1 and a pole at minus 3. Those are both in the left half plane. This system is stable. What's the order of this system? 2. So the A is a 2 by 2 matrix. It's a second order system. You have two poles. Is this a single input, single output system? How many inputs do you have? How many columns are in B? How many columns are in the B matrix? 1. So you have one input. How many rows in the C matrix? Rows in the C. 1. So you have one output. It's single input, single output. You know a lot just by looking at this system that somebody has given you. Let's now sketch the block diagram. And this one will be an all integrator. Block diagram. How many integrators do we need to introduce or have in this block diagram to model this system? How many derivatives do you have that you actually need to integrate to generate? Your block diagram is really a way to simulate or evaluate or describe the dynamic behavior of your system. You have two. You have an x1 prime and an x2 prime. Now, not knowing too much about your system, you may not know which way to put or where to put the different x primes, but if you look at this state space representation, x1 prime is made up of two pieces, minus x1 plus 2x sub 2. So let's put x1 prime over here because it's going to be made up of whatever I just said. It was minus x1 and 2, whoops, times 2. So I need to see, you never know what's going to happen, so I needed to squeeze a 2 in here. So there I need that 2 to be multiplying x sub 2, because here is x2 prime. I needed 2 integrators because I had an x1 prime and an x2 prime. And so far, I've actually described or interconnected enough of this to create x1 prime in terms of x1 and x2. What was x2 prime? Did it have an x1? No, because the 2, 1 entry is 0. So there's no x1 directly feeding into making the time rate of change of x sub 2, or x2 prime. x2 prime is minus 3x2, so we pull from x2, scale it by minus 3, is there anything else making up x3, or I'm sorry, x2 prime? No more states, but we do have an input, don't we? We now have u also making up a part of that. And it's scaled by a 1. So if this was some other value and not a 1, then we would need to put a gain in here. Maybe I should just make that explicit. Let me there's u of t with a gain of 1. If it was a 6, you could have replaced that 1 with a 6. Now that block diagram has now completely described the x prime equal ax plus bu. What we now want to do is create the output equation that's built from the states and the input. We need 4 x1s. So now I'm building up the output. And I need 5 x sub 2s. So I come over here and I pull that off before it gets scaled. There's x2. I scale it by 5. And there's my block diagram. In which domain am I living in this block diagram? Time domain or frequency domain? Time domain, because I have t for arguments and I have integrators, which are time domain operations. This is a time domain block diagram, and it's an all integrator block diagram. If I was really feeling generous and I said, give me a frequency domain block diagram, could you do that now that you have this sitting in front of you? Yes. Now what do you need to do to get into the frequency domain? We simply need to remember that the operation of integration in the time domain is equivalent to 1 over s in the frequency domain. And that's the only change in the block diagram that really has to be made. All the other interconnections can be left alone. Gains and summing. Are there any questions with that? Exactly the same block diagram. If you could simply make a copy of that time domain and paste it, and then just erase the integrators and replace those with 1 over s's, and all of your signals, change those arguments from time to the s domain, you now have your frequency domain description. We've looked at state space, block diagram. Now let's look at a transfer function. G of s is y of s. In this case, our input is u of s. And so we could do the block diagram algebra like we started with in today's lecture. But let's do it a little differently. Let's do it with a technique that's described as Mason's gain. But before I do that, is there another way that we could find the transfer function g of s with the information that we have from this example? Cheer number 1, right? Cheer 1 could give us, I was never a cheerleader, okay, so I apologize for that poor interpretation or animation. You could find g of s from cheer number 1, where we used g of s is c si minus a inverse b plus d. You have all of those from the very beginning in our state space representation. And that would require a symbolic matrix inverse of what size? 2. It's a 2 by 2. The I matrix there is what? 2 by 2 with 1s on the diagonal and 0s on the off diagonal. So you could do that, and I think you should be able to do that. But let's now look at Mason's gain approach. And Mason's gain, the big thing here to get started is to identify paths and loops in your block diagram. Paths are all of those unique paths from the input that, without crossing itself, ends up at the output. Meaning, I could create one path that went straight through there. And I would then identify the gains and all of the, let's say, rational expressions that make up that particular transfer or that particular path. If I just follow from U to Y, what do I pick up? I pick up a 1 over S, so that's a part of my path. I pick up a 2, so I now have 2 over S. I pick up another 1 over S, I now have 2 over S squared. And finally, it scales by 4, so I have 2 times 4, or 8, over S squared. That's path number 1. Does everybody see path 1? Going from input to output. P1, and so now I need to label this. P1 is now 8 over S squared. And that was coming from that yellow highlighted path. I just pick up all the gains and transfer functions that occur as I go from U to Y. Is there another way, is there another path to go from U to Y? So now if I come along here and if I go up and then back down, do you see that that's also a path? and it's unique from the previous path. What's path 2, the blue path, as far as an expression? You just pick up all of the pieces that you encounter as you navigate that path, and you now have 5 over s. That's path 2. P sub 2 is now 5 over s. And that one was coming to us from the blue highlight. Now we want to, those are paths labeled with the P's. We want to now look at loops. So we come back here and we try to find loops in this block diagram, and loops are any continuous path that doesn't cross itself but yet returns to the same point where you started. I don't know, I'm getting creative, so I'm trying to find a way to do this. Do you see that this is a loop? Do you see that this is also a loop? So this particular block diagram doesn't have too many weird loops, but you can encounter some very interesting loops, but this one is pretty generic. But it has 2 loops. I can't do something fancy. I can't do this because I have to obey the arrows. I can't go against the arrows. So there's no loop in that last one that I just drew, and hopefully that good will allow me to erase. Let me call this loop 1, I hope, and this loop 2. I've identified 2 paths, and in this case, 2 loops, but I don't always have to have the same number of paths and loops. I could have 5 loops and 2 paths. Loop 1 was minus 3 over s. You have to keep track of the negative signs or the scalings. And loop sub 2 minus 1 over s. Now that we've identified those, now it's fun. Now we need to create the determinant. And the determinant, I just enjoy this one. So I'm going to call this delta. And this is now just a combination of what we've already identified. It's just a combination of our loops. First, we have a 1. Then we subtract the sum of all of our loops. How many loops did we have? So we now just take the sum of those and subtract them, and keep track of all the minus signs. The next piece is we look at our loops and we say which of these loops are non-touching. And if they're not touching each other, then we form their product, and then we take the sum of those pairwise non-touching loops. What? So this is just L1 times L2 in this example. This is the sum of non-touching, and I'm going to say NT, pairs of loops. The first piece that we subtracted was just the single loops. The next piece took them in pairs and took their product and summed those up. Then we just keep going and we alternate the sign. We have minus, we had pairs, now we have triples. So if we had 3 loops, we form the product of those 3 if those 3 do not touch. So we have the sum of n non-touching triples plus the sum of non-touching quads. 4 loops that don't touch, and we form their product. This doesn't even exist in this example, does it? How many loops did we have? 2. So we couldn't even talk about a triple. But I'm giving you the general formula. And notice that I'm alternating signs. Then what would I do? If I had as many as 5 loops, and they're all non-touching, then I would form the product of those 5 and subtract it. And if I had 20 loops and I had a few of those that came in 5 sets of 5 that didn't touch, I would form all of those sets and subtract those. Yes? So we look at, the question is, when we have a collection of loops that don't touch, and we actually have, what, three loops? So let's say those 3 loops are non-touching. Then what you have to do in the pairs of loops, you have to say 1 and 2 are not touching, 2 and 3 are not touching, I don't have enough fingers, and 1 and 3 are not touching. So those would all be pairs of non-touching loops. But then you would also need to include this triple, L1, L2, L3, that didn't touch. Did that help? Question? So a loop touches when, I should have maybe had an example, but that will be for homework. But let's say that this, pick the right one, if this one came and, well, let me do a different color. Let's say that I actually had a loop that did this. Then that purple touches loop 2 and loop 1. But loop 1 and loop 2 do not touch. Meaning if I had a path that was from here to here, I would now have that purple loop, would I not? And in that case, I wouldn't have a triple of non-touching loops. L3 would be touching L1 and L2. Does that help a little bit? It gets a little weird. So we wouldn't have, in that example that I just illustrated, we wouldn't have a triple, would we? We would have 3 loops, so L3 would appear here. Whoa, have to watch what I have in my hand. L3 would have appeared in that sum of loops, but it wouldn't have appeared in a pairwise product because it touched L1 and it touched L2. So it would appear in the sum, but it wouldn't have appeared in the product anywhere. Not even in the pairs, because L1 touched L3, L2 touched L3, so you wouldn't have it in that product of pairs of non-touching loops. But you would still have L1 and L2 product. Let me keep going. So you just keep going until you run out of loops. If you had 10 loops, you would be looking at all of these plus, minus, non-touching 9s, 10s, etc. But typically, they don't all non-touch. So what's my determinant? In this example, my determinant is 1 minus L1, but L1 was minus 3 over S, so I have plus 3 over S, and L2 was minus 1 over S, and I'm subtracting that, so I have 1 over S, and then I have minus 1 over S times minus 3 over S, or I have 3 over S squared with a positive sign. Those are my 4 pieces, and I can combine the middle two so that I have 1 plus 4 over S plus 3 over s squared. So that my determinant is now, if I put them all over a common denominator, it's s squared plus 4s plus 3 over s squared. Those are my determinants, and maybe you remember something else that sort of accompanies determinants, cofactors. So let's say that we start with our original determinant, which was 1 plus 3 over s plus 1 over s plus 3 over s squared. And this was really 1 minus L1 minus L2 plus L1 L2. Now, how many paths do we have in this example? 2. So we're going to have 2 cofactors, 1 for each path. And the cofactors arise out of the determinant, or what's left from the determinant. Cofactor 1, what we do is we go back to our block diagram and remove path 1. So virtually erase everything that's on that yellow path. And if that disconnects any loops, then those loops fall out of this determinant expression. When I erased path 1, did that disconnect loop 1? Yes. So loop 1 is those two. So those get eliminated. Did it eliminate or disrupt or disconnect loop 2? So what's my cofactor? What's left from my determinant? 1. That's my cofactor for loop or for path 1. Cofactor 2. Now, eliminate or virtually erase path 2. And then in your determinant, get rid of those loops that were disconnected. Was loop 1 disconnected if I virtually erase path 2? Yes, so now anything that had loop 1, I can get rid of. If I eliminate or virtually erase path 2, did that disconnect loop 2? No, so I keep loop 2, and if anything else was remaining, so now in this cofactor, I have 1 plus 1 over s. Those are my cofactors. You have one cofactor for each path. And the cofactors are found by eliminating the path, and if that disconnects any of your loops, you get rid of those from your determinant expression. Now you're done. Now the transfer function, g of s, is path 1 times its cofactor plus path 2 times its cofactor. And you just keep going until you have eliminated all of your paths, and you divide by the determinant. That's your transfer function. So in our case, our transfer function, path 1 was 8 over s squared times its cofactor of 1, plus path 2, which was 5 over s, times its cofactor, 1 plus 1 over s, all divided by the determinant, which is s squared plus 4s plus 3 over s squared. Now do you see the ratio of ratios? And you can clean all of this up with just some algebra. Meaning, this is now 8 over s squared plus 5 over s plus 5 over s squared. And downstairs we have s squared plus 4s plus 3 over s squared. And if I change this to multiply by 1, s over s, I have a common s squared in all terms in the numerator and in the denominator, I now have 8 plus 5s plus 5 over s squared plus 4s plus 3, or I have 5s plus 13 over s squared plus 4s plus 3. There's my transfer function. Now you know that transfer function can be related to y over u, and from that we'll find our differential equation. But apparently the phone rang, so we're finished.